comes from the function applications worksheet that you received the other day in class. So the key with all these is to create the diagram. In this initial case, we have an open top box. So we're going to draw a three-dimensional box. Now it can appear to be a cube, but remember it all comes down to the labeling whether it actually is a cube or not. But the idea is to figure out what the diagram looks like. So here is our three-dimensional figure. What do we know about it? We know it has a square base. So if it has a square base, we need to call them the same thing. It's constructed from sheet metal. So in other words, it came from a rectangular piece and it's been cut and welded together, whatever the case is, in order to make this box that has no top. And that sheet metal was 2 square meters. So the area of the rectangular sheet was 2 square meters, cut up into those 5 pieces, the 4 sides and the base. That area still needs to remain 2 centimeters or 2 square meters. So we're expressing the volume of any rectangular prism is the area of the base, which in this case is x squared, times the height. Now that technically is a function of x and h, so I'm going to rewrite this in function notation as volume of x and h, as opposed to like f of x or h of t and different things we've seen before. V of x and h. Now the other piece we know is that the surface area has to be 2 square meters. That's given right here. That was the area of the sheet metal, but it has now become the surface area of our prism. And we know surface area is found by adding up the area of all, in this case, 5 surfaces. So we know that the area of the base plus the area of the 4 sides must total 2 square meters. Well, remember, we want the volume as a function of the width. In other words, x. I need to find a way to write v of x. Well, I'm pretty close already. I have x squared, but I need a new height. I need to find the height in terms of x. And that means we can simply take this equation right here and solve it for h. And substitute that in for h. And now I have the volume in terms of x. So that's part A. Part B is finding the maximum volume of the box. Well, we have to rely on a calculator at this point. However, remember all the strategies we have for finding a nice viewing window. The realistic domain of this function. X is our independent variable, and x represents the width of the base of this box. We cannot have anything smaller than or even equal to 0. And the biggest our width can be, look at the zeros of our function, right? We have x squared equals 0, and we have 2 minus x squared equals 0. This is how we got x equal to 0. And through this method, we'll get x equal to plus and minus the square root of 2. However, we clearly know that negative square root of 2 is not an option. So our domain is 0 to 2. As far as my range is concerned, obviously the volume can't be 0. And if you recall, our strategy for finding an estimate of the height was to take the middle value here. Right? We have the ability to curve sketch this. We know negative root 2, we know 0, and we know positive root 2. We also know this is a negative quartic function with a double 0 at 0, because x squared equals 0. So my graph is coming through, sorry about that, negative quartic. So it's upside down. My graph comes through like this. But the only part I care about is the part that deals with positive volume. And that's right here. So if I want to estimate the highest y value, I'm going to pick something in here. Remember, the square root of 2 is approximately 1.414. So if I pick something like 0.75 and I plug it in here, I'm going to get a nice y value for my range. Okay, and you can do that on your own at this point. Of course, then we're going to do second calc, maximum, left bound, right bound, guess. Let's look at problem number 2 and get you started on that one. In problem 2, a bike path is traveling north and south. North obviously is up here, south is down here. It goes over a river that goes east to west. So here's west, here's east. And they intersect at point O, so we'll call this O. At noon, a biker leaves O traveling north at 12 kilometers an hour. So somebody's going north at 12 kilometers per hour. At the same time, a boat is 25 kilometers east. It's out here at 25, and it's traveling west. It's heading back towards O at 16 kilometers an hour. So we want to find the distance between the biker who's going north and south and the boat who's traveling west. So I think intuition can show you that that is going to be a triangle. The biker is going to be up here somewhere and the boater is going to be down here somewhere moving. We don't know where because we don't know how much time has elapsed. So we're looking for that distance. So if I pull out that triangle and start labeling some pieces of it, that's what I'm looking for. Well, this is the biker. What is the length of this side? The biker is traveling at 12 kilometers an hour. So after 1 hour, the distance is 12. After half an hour, the distance is 6. After 2 hours, it's 24. So what's going on here? Well, every hour, he's traveling 12 kilometers. So his distance as a function of time is 12t. The biker's distance as a function of time is 12t. Where the boater's distance as a function of time, I can't use B again, so I'm going to use, I don't know, the boater, we're going to do a speedboat. So S, his function of time is a little different because he's starting 25 kilometers away and he's getting closer. Every hour he gets 16 kilometers closer. Every half hour he gets 8 kilometers closer. So he's starting all the way out here at 25, but he's getting closer. So his function of time is 25 minus 16t. At that point, we can use the Pythagorean theorem to find the distance as a function of t and only t at this point. Okay, square root of, and do your Pythagorean theorem. And again, remember, when doing the graph, you're not necessarily going to be able to sketch this one nicely, but you still have some information that can give you a realistic domain, and therefore you can plug in to find the realistic range. Think about what's happening here. This boater is going to get back to the origin in, I don't know, roughly an hour and a half, right? Because an hour and a half takes him 16 and 8, 24 kilometers. So it is safe to say that the domain cannot be anything less than 0 hours, because time has to happen for people to get closer to each other in this case. And if I would actually solve this, I get 25 minus 16t equals 0, which means t is 25 over 16. And you'll notice that is roughly an hour and a half that we approximated. Now we know they can't be any closer. Or once they get to this point, once the boater gets here, everything's going to be further away because this guy's continuing to go up and this guy's going to continue to go out. So the distance will be further than the vertical distance would have been here. However, when they're over here, they could still be closer because this biker has not traveled as far north as he previously had. So you need to give an approximate range. Of course, we can't have a distance of, well, I guess we could have a distance of 0, so open or close is kind of irrelevant. And you're going to pick your value somewhere in the middle to give yourself an approximate value for the highest range right here, and then you're going to plug your equation into the calculator and solve for closest, so you should be thinking minimum in this case. Let's move on to number 3. I think you have enough information for number 2. Um, Number 3, very, very similar to number 2. And in fact, I think it's similar enough that I'm going to let you do that completely on your own. Number 4, again, very similar to number 1 in this case. The difference is you're talking about cardboard, so you're not going to be able to weld this together. So in this problem, you're going to be thinking about that piece of cardboard and having to cut some corners out of it. Because you really don't want to use duct tape to tape this box together. It's not going to be extremely sturdy. And just remember you're cutting out an unknown value from each corner. And maybe that was something I should have added into the directions here, but I think we did enough of these last chapter where you kind of are thinking about that already. So this one is a prime curve sketching, identify a realistic domain and range, and I think you can reference anything from last chapter to finish this one up. I think I got a good setup there for you. Now, a box with square base has no top volume. With no top, has volume of 8 cubic meters. The material for the base costs 8 square meters. The material for the sides costs 6 square meters. $6 per square meter. Express the cost as a function of the width. So again, we have a box. It does have an open top, so we're looking at the same diagram as problem number 1. Sketch it out here real quick. Hopefully you guys are getting a little better at creating three-dimensional figures. As I mentioned that, mine is horrible here. At any rate, we have a volume, and this guy has a square base. Is that true? Yes, a square base. So x, and of course h. Now we know volume as a function of x and h is x squared times h. We saw that back in problem 1. The difference here is that we're told the volume. So we know that 8 is equal to x squared h. And the material for the base costs $8 per square meter. The material for the sides costs 6. So in this case, our surface area is how we're figuring out the value. So the cost is going to be a function combining volume and surface area. So my cost equation, we'll put our variables in a minute here. Our cost equation is $8 for the base plus $6 for each of the 4 walls or sides. Now this is a function of x and h, and that's a problem. We want this as a function of just x, the width of the base. So very similar to problem number 1, you need to finish, and instead of having volume in the terms of x, we want cost and only cost in the terms of x and only x. So I need to find a way to get rid of this h, and conveniently we have another equation that has h in it. So maybe that sets up a light bulb. As I'm trying to draw a light bulb, it's going to turn out to be a heart. Let's see if I can do a light bulb here. Drawing is certainly not one of my better skills, but there you go, a light bulb. Hey, light bulb, I got an H here and I got an H there. Ding, 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 ding. I know what to do. I'm going to finish this and get a perfect. Nice of you to listen.